Okay, well, I want to welcome all of you to the second annual Summer Intern Lecture Series. This is something we started last year, and we got to give all the credit in the world to Scott. We've got a great speaker today. It'll be followed throughout the summer by three other speakers, three additional speakers as we go. We hope that you attend them all. We're really glad to have an audience actually in person. It's nice to see people and faces. That's a wonderful thing, and it's a great sign. We're also glad to have folks on the web so that you get an opportunity to hear from the speaker that we have today. And now to that speaker, I am just incredibly pleased to introduce John Till. Let me tell you a little bit about him. He is the president of Risk Assessment Corporation, a company that he actually started. John is a retired Rear Admiral with the U.S. Navy. He had a distinguished military career. As they say, freedom isn't free, and John certainly paid part of our price to keep us free and allow us to do the things we do. I think we should just give him a hand for that. He graduated from the U.S. Naval Academy, got a MS, a Master's in Science from Colorado State, and got a Ph.D. from Georgia Tech. He started his non-military career at Oak Ridge National Laboratory, where he did a lot of work on mathematical modeling and studying dose in the environment and then how it relates to people, how it affects people. He actually wrote a book entitled Radiological Assessment, a textbook on environmental dose assessment. It's still one of the major references in this line of work. So he's had a tremendous career, many accomplishments throughout. A couple that caught my attention, he led a team of 18 scientists who studied radiation dose to the public from the Hanford Reservation. He also was the chair of National Academy of Science Committee that reviewed the dose reconstruction for our atomic veterans. He and his wife Susan now live at actually their family farm in South Carolina, where they grow corn and soybeans. It's interesting. I was born and raised on a farm. We grew corn and soybeans also. However, he also grows pecans, and we didn't do that. However, I will sit down. If you want to make a pie, I will come on over and I'll sit down with you. I am pleased to welcome John Till. Thank you. Thank you very much. Let me get this to you. Okay. You can do that. Let's see.
Well, that was just terrific, Phil. I really appreciate it. And you come to my farm and I'll give you all the pecan pie you want. I'm really grateful to Savannah River for inviting me back over. Last year I gave the seminar from my office, and when Scott invited me, he said, well, you can come over or you can give it in your office. And believe me, it is such a pleasure to be back here, to see all of you young people sitting out there. I hope that what I talk about today is something that you can carry away in some small piece in some way, that this will make an effect on the rest of your professional lives. The title, I had a good time thinking about a title for today, and I'm going to talk about 50 years of risk assessment. It just turns out that when I started into this profession, it was 1971, and I went into Colorado State, and that was sort of, quote, the beginning of my professional career. It has been 50 years ago that I did this. And what I'm going to do is just highlight what I think the key changes have been in this profession over the 50 years, okay? As I talk about risk assessment, there are all kinds of risk assessment. What I'm going to talk about is when radionuclides are released to the environment, what is the dose and what is the risk to humans? When I began, it was very not a very well formed profession, and I'll come back to that in a few minutes. I'll talk a little bit about the history of myself and how I wound up here. Phil did a great job of reviewing that. I'm going to go at a very high level, and it's going to go fast. So buckle your seatbelts. When I talk, I really enjoy telling stories. And I'm going to venture off into stories as I go through the presentation. I want you to know they're all true. Every story is true. And how many stories I tell depends on how much time we have. As Phil mentioned, I am a retired Navy guy. And let's see here. Yeah, there we go. There we go. This is my first slide, so I'm going to talk a little bit about Navy. And I just wonder, out of this audience here, does anybody know who this is? Okay, a couple of you do. This is Admiral Hyman G. Rickover. And Admiral Rickover was the father of the nuclear navy. Admiral Rickover was not a very friendly person. He was not well liked, not by his fellow admirals, not by the congressmen that he interacted with, or the senators, or even the President of the United States. Admiral Rickover was just not a very friendly, well-liked person. But he had a vision about a nuclear navy that to this day has never been outdone by any country, and we have the finest nuclear navy still today, and it's all because of this gentleman, this now deceased Admiral Rickover. Everybody in his program, every officer had to have a personal interview, and I had mine. And that's another story. I'm going to skip that one, but I'm going to tell you something that happened to me. In the Navy, when we talk about rigging a ship, it means that we take certain actions aboard ship to prevent things from happening. All right, so we can rig for foul weather, where we close certain doors, watertight doors on a ship. But we also, in the Navy submarine program, had what's called rig for Rickover, because he was insistent on certain things being done aboard ship prior to his arrival. So that's just a list. I don't know if you can read it, but I'll read a few of these to you. 2 full sets of khakis with insignia. Shirt size 1432, trousers 30, length 29. Grapes, apples, fresh orange juice, ship stationery, several pens, no ballpoints, pencils, and line pad. The latest New York Times. 3 pillows on the bed, 1 blanket. Now, I'm not going to go through all of this. It was 3 pages of a list like this. Now, who do you think aboard my submarine had trousers, waist 30, length 29, and a shirt size of 1432? I did. So the captain assigned me the job of rigging for Rickover. I don't remember all of the details of this. I remember I had to give my own uniforms, khakis, okay, which I never got back, by the way. I never got them back. I remember that I had to figure out a way to get the latest New York Times flown from New York down to Pascagoula, Mississippi. I don't recall how I did that, okay, but somehow I managed it. Nevertheless, okay, this was what Rickover, he expected perfection out of everybody, but he taught me so much. And one thing I'll leave with you is that because of the Navy and because of what he taught me, my scientific career took a little broader perspective than some people. Because he taught you in the Navy, when you're an officer in the maneuvering room of a submarine, that your job is to see the big picture. You want to see the steam panel, the reactor panel, the electrical panel, and know what's going on all of those panels all the time, so you know what action to take. And so my career is broad as a scientist. And you'll see as I go through my career and how things happened, that Rickover influenced my professional scientific career tremendously. Okay, so from the Navy, I went to Colorado State, to Georgia Tech, as Phil said, and then as a graduate student, went up to Oak Ridge for my dissertation work. I grew up on a farm about 40 miles from here outside of Orangeburg. It was a big dairy farm. There were 3 uncles and my granddad who actually developed this farm. And I was very close to it. I was very close to this. I spent all my summers there as a kid. So in the mid-70s, I had a couple of uncles that died suddenly, and the farm collapsed. And this is while I was at Oak Ridge. I had just finished my doctorate degree in 1976. I was off to a great start there at Oak Ridge, and I had to make a big decision. It was either go save the farm or take my professional career and stay at Oak Ridge. I decided I was going to do both. Now, every single relative, every single friend that I had at the time told me, John, you're crazy. You can't move in the middle of the country. You can't try to recover a dairy farm and continue a scientific career. I'm a very hard-headed person, and I didn't listen to any of them. So I moved back to the farm in 1977, was able to turn the dairy farm around, eventually sold the cows, but I live on 1,000 acres that to me is paradise, and I absolutely love it. At the same time, I created my company in 1977 called Risk Assessment Corporation. I didn't know how I was going to find work, okay? There wasn't a lot of work out there for people in the middle of the country, but some things happened. The late 70s, technology was changing rapidly. In the early 80s, we had microcomputers, we had Federal Express, we had fax machines, and all of this just gelled together for me. And the one thing, the one reason why I think people came to me for work was because I was independent. I wasn't connected to any other corporation, any government organization. I was independent, and that helped me tremendously. Okay, so I formed my company that exists today, and this is Risk Assessment Corporation. It's a virtual company, and virtual all the way back into the early 80s, okay? My team lives all over the country. They all bring a certain specialty to the team, okay? Because this is what risk assessment is all about. We meet about 3 times a year, and as I go through these projects, these opportunities that I've had in my career, these guys, in part, are responsible for so much of this work, and they are the best scientists in this profession in the world, in my opinion, okay? And I love them all. And I'm going to just talk, this is an equation that explains what I do, and I've started from the very beginning in breaking this science into different disciplines, all right? So risk is really the source term, radionuclides, how much, what's the temporal distribution and so forth, the transport, atmospheric, aquatic, groundwater, whatever, exposure, how much do people breathe, how much do they eat. If you know that, then we know we can convert it to a dose. If we have a dose, we can convert it using a risk coefficient into risk. So just keep this in the back of your head, because all of the studies that I'm going to talk about involve elements of this equation. And at the end, uncertainty, validation, communication, and public participation. Okay, so let's get going. This is going to be, like I said, a high altitude trip. We'll talk about the 1970s. And I'm going to talk about this because this is where I began, and I titled it as Disparate Sciences, okay? And let me tell you why. At Oak Ridge, I was fortunate enough to do some incredibly unusual work with unusual radionuclides for a dissertation, but what a place to go. If you ever have a chance to go and work at a national lab, including Savannah River, it'll give you some opportunities that you'll never have anywhere else. Never, not like a university at all. And that's what it did for me. One of the first things going on was I worked with a guy named Bob Moore. He was one of the original developers of what's known as the air dose computer code, which we used at that time to calculate doses to people from releases to the atmosphere. It was a simple Gaussian type model, nothing sophisticated about the code, but it taught me a lot. And Bob taught me a lot. Everybody know what a punch card is? You guys know what a punch card is? Some of you are shaking your head, some of you not, right? This shows you how far back I go. So the codes were all run by cards that you had to punch to key in certain commands, right? And so you'd have a code like AirDose, and you'd have a big stack of cards. Now at Oak Ridge, all of the computers were down at the other end of the laboratory, right? They were controlled by computer sciences. You know, these are the big guys. You walk in with your punch cards, you know, put them on the desk, and then they're not too friendly there because they know they have a lot going on, and they know they got you, okay? So you have to be very friendly when you go in. So they'll run your code overnight, hopefully. And hopefully, if you don't have one thing wrong, if it's perfect, you can get your printout the next day. If not, you go back, you start over, take your cards down the next day. That's how it all started. I want you to keep this in your heads as we go through this, because of the way we do things now, it's phenomenal. This is the dark ages, okay? At Oak Ridge, we were at this time in the late, in the mid 70s, so forth, we were thinking about nuclear and the power, energy that we could get from it. We were looking at something called the Clinch River Breeder Reactor. That was one of the huge investments from the Department of Energy. We're looking at breeder reactors. And I was in charge of, I can't say I was in charge of anything, to be honest with you. What I was doing was working with people on the environmental impact statement, right? Now, let me tell you a little story. At the time, what we did was to try to find where outside of the reactor the person who would be the most exposed to any radiation, should radiation come out the stack. That was called the most exposed individual, the MEI is what we call it. And so what we did, we would take a source term, and I'd go over to the Chem Tech division and get the source term and bring it back, and we'd put it in. I'd have to go over to the Environmental Sciences division and get the latest parameters for plant uptake and so forth, and we'd put it in the code and so forth. And then we'd come out, and sure enough, it turns out that the MEI was located to the west and a little bit to the south of the laboratory, and it would be along the river because we had to take into account the river pathway. So I'm sitting there with my colleagues one day, and we've got this pinpointed on a map, and I said, you know, does anybody really live there? And they all said, well, it really doesn't matter. You know, it's just a hypothetical person. But I said, but what if somebody really lived over there? Nah, John, nobody's going to live over there. That is close to the boundary of the laboratory. It's wilderness area. And I said, well, I'm going to go find out. And they said, okay, I wanted to know who wanted to go with me. Nobody wanted to go with me, so I got the lab truck one morning. I drove out to the West Laboratory and cut in alongside of the river. And I'm going down about 2 miles on a little rugged road. And sure enough, there's a little cabin on my left. And there was a guy sitting on the front porch. Now, you got to admit, you know, I'm a city slicker, okay? And I'm going out thinking, I'm going to just go around and talk to these people. And so I pulled up in the guy's yard. He was sitting on the front porch, got out. I go up and I say, you know, I'm from the laboratory, and I'm a scientist, and I'm really trying to find out the kinds of things that you eat, and do you fish from the river, and so forth. And he kind of, you could tell he was a little irritated. Okay, well, why are you here? Why are you asking me these things, all right? And he didn't say much. Started to get a little bit nervous. He said, well, I'm going to go inside for a minute. He left me sitting on the porch. I didn't know if he was going after a shotgun or a banjo. I really didn't have any idea what was going to come out of the door. And he actually brought his wife out. And he said, I don't remember her name. He said, Mildred, he said, this fellow here wants to know a lot about our private lives and what we eat, and do we fish? And she said, well, why don't you invite him in? So they invited me in to a little kitchen table. She happened to have some biscuits there and some jelly. And she said, you know, why don't you just have some fresh biscuits? But we started talking. And then it started to flow out. And yes, they do have a garden. And yes, they do fish the river, okay? And they were almost self-sustaining there with their food. And of course, if you know this, that means the doses are going to be higher, right? And then she brought out a jar. Looked something like that, only it was much darker, much bigger jar. And she said, well, we can catfish. Would you like to try some? And I was caught in a little bit of a jam there because, like I say, it did not look too appetizing. And I said, you know what I'd like to do is take a jar back to my colleagues. Why don't I do that, you know? So I took my jar back to the colleagues, put it on the conference room table, told everybody about it. And I said, why don't we just try it? Absolutely not, John. We cannot. We are not going to open this can of catfish and try it. So I let it sit there for a little while, a couple of days. And then I came in early one morning and I opened the jar and I took some out and just threw it away. And then I closed the jar, but you could see that some of it was gone. When they came in that day, they were shocked. Who ate the catfish? So I told them that I had tried it. Now, you talk about a credibility builder. That really got me some credibility with my colleagues at Oak Ridge. But anyway, one other project that I worked on at Oak Ridge going on, which you guys will think is absolutely insane, it's called Operation Plowshare. There was a time in the 70s when we thought we could take nuclear weapons and explode them, and we could do things like stimulate natural gas. We could expand the Panama Canal. And there was a guy named Charlie Barton there who did a lot of this work, early work, trying to figure out what doses would be to the public if we did this. And I remember in the late 70s, they killed the project. And I went up to Charlie and I said, Charlie, why did they close down Plowshare? And he said, bananas. He said, because of bananas in the Panama Canal. That was the reason they closed it down. And that there was an outrage when the public found out that even though the doses were small, we were going to explode these nuclear weapons, that these radionuclides were going to get to them in some form, even though the doses were small. So that killed the Plowshare project. Now we're going to go out of the 1970s with one more event, and that's 3 Mile Island. Huge, okay? I did some work on 3 Mile Island. I worked with NCRP and some really fine scientists, because the biggest problem we had with TMI was, what are we going to do with the contaminated water? Huge amount of contaminated water. And we really had two options. One is dump it in the river, and one is evaporate it. We wound up doing some of both. But this was one of my first opportunities to take my science and apply it to a real world problem. And by the way, I'll mention this, but when TMI happened, you may recall, I know you youngsters don't know about this, but we evacuated 140,000 people. And we did that because some calculations were made that led the NRC, Denton was the chairman of the NRC, to believe that doses right at the fence line and not far from the fence line would be significant and could expose the public significantly. The truth is, they had made an error in the calculations by a factor of 10. Now, as I get through this lecture, at the end, I want you to see how far we have come in terms of being able to make an instant decision about doses if you have a release, okay? So let's go into the 1980s, and I call this consolidation and application. I was so lucky. In the early 80s, I was called by NCRP that's the National Council on Radiation Protection and Measurements, and asked if I would co-chair a report that discussed the transport of radionuclides in the environment and how we calculate doses to people. These guys you won't know because most of them are dead now, but these are the pioneers. These are people who were long before me really set the stage. As the metaphor goes, you know, I'm just a scientist who's ridden on the shoulders of giants. And these are the giants. And I won't point all of them out, but for some of you out there watching, from left to right, I'll just go through this quickly if I can. Owen Hoffman, Dick Foster, Yuk Ing, who did much of the plant uptake factors that we do today, used today, Dave Baker, Gordon Blaylock, Bill Templeton, Dave Waite, John Witherspoon, Frank Gifford on the far right. If any of you get into meteorology, you're going to hear about Gifford, Pasquale coefficients, and Frank Gifford, just a wonderful scientist. Ivan White, Dave Edgington, Dick Cadell, and Bill Robinson. All of them had their own disciplines, and they were the top in the field. I was just a 33-year-old guy. Why did they ask me to chair the committee? I have no idea, but what an incredible opportunity that was for me. So that led to the publication of this report, and as Phil had mentioned, I took that idea a little farther because I knew we needed a textbook in this science, and the whole idea was to pull these different disciplines together. So one of the things going on in the 1980s, and it had happened previously from 1944 to 1963, we set off hundreds of nuclear weapons to test, okay? Began with the Trinity test in 1944, but we had a shot in 1953 called Shot Harry that made a lot of noise, all right? What happened was it was a dirty type explosion, a lot of radionuclides released to the air. The wind changed directions suddenly, 180 degrees, deposited a great deal of radionuclide material in the southwest part of Utah, particularly around the town of St. George. And people began to worry about this. Even though the shot was 1953, they began to worry about how this might cause cancer. And so the National Cancer Institute, the National Cancer Institute funded the University of Utah to look at the exposure to people, particularly in southwestern Utah. So now what's happening to the science is that we're calculating real doses to real people by the mid-1980s, and not just a single person. We had a thyroid cohort epidemiological study, 345 children. We had a leukemia case control study. 1,177 cases of leukemia, 5,330 controls, and we had to include uncertainties. For its time, this was the largest epidemiological study completed, particularly related to the atmospheric testing in the West. So what did we find out? We found out the leukemias, there were no leukemias, it was not significant. We found that there was a significant increase in thyroid nodules, but not thyroid cancer. And it was a weak statistical result. We also used surveys to go out and find out exactly where people lived, exactly what they ate, and so forth. At the time, this study really set a new paradigm for risk assessment. I'm going to mention Chernobyl in a moment, but Chernobyl and Hanford used a lot of what was developed for this study. Okay, 1986, April 26, you've all heard about Chernobyl. I'm not going to spend time on this. I didn't work on Chernobyl. I've focused my entire career on studies in the United States. Nevertheless, here we are at the end of the 80s. We had TMI at the end of the 70s. We've got Chernobyl at the end of the 80s. Who wants to get into this profession? I mean, nobody. For me, it was a low point. I didn't know where I was headed over on the farm. I didn't know if there would ever be any more work. How wrong I was. In the 1990s, we went through a period of historical dose reconstruction and what I call rebuilding, I should say, credibility and trust. Okay? Let me talk briefly about that. Hanford, and for those of you who were here last year, you've heard this story before, okay? But it's a really important part of my life because it changed me as a scientist and the way I look at my work and my responsibility as a scientist to communicate what I do to people who are exposed. I took that all personally. But let me tell you what happened. Okay, back in the 1940s in particular, from about 1944 until about 1950, Hanford is located in Washington State, southwestern Washington State on the Columbia River. This is the N reactor. This is where we made the plutonium for the first bomb. But during that time period, we released huge amounts of iodine-131, in particular, to the environment. 800,000 curies, roughly, were released between 1944 and 1949. Now, that's a lot of radioiodide. It was done deliberately because at the time, we didn't understand the pathways. At the time, we were in a crisis because of the war, and we were in the Cold War, okay? So we released this material. Now, all of this was classified for many years, but people in the area began to hear about these large releases from Hanford, and nobody would talk about it until ultimately the governors of Oregon, Washington, and the Department of Energy got together and decided that we're going to open the books and we're going to do a study on these releases. So I was fortunate to be called to be one of the scientists to work on this study. It was a really eclectic group of people. It's not the kind of people, if I had made the decision about who you pick, you know, an agriculture guy, I'd want a guy that really knew dairy pathways and so forth. But we had an agricultural economist, all right? We had a meteorologist who was really more of a weather meteorologist, not a dispersion expert. On the other hand, this is the cast of the dice that we were given. We didn't know one another beforehand. For some reason, they asked me to be the chair of the panel, and this panel made history. It made history. We were going into a study we knew was going to cost $25 million or more, and DOE had that budgeted. Battelle Northwest, a major laboratory, kind of like Savannah River, was to do the technical work, It was our job to direct the study, okay? And this was tough. This was tough. But here are some things that we did that really changed the way that we do this science today. I don't have time to go into them. I talked more about this last year. Independence. We got ourselves out of the Battelle, who are the technical folks who are paying our salary, and that can't be. We were not independent. So we eventually took the study, and with the support of Senator John Glenn, we were able to get all the money transferred to the Centers for Disease Control in Atlanta. Independence, huge in terms of building trust and credibility. Transparency. Transparency, think about this. We're working with classified materials. You know, we're scientists. Leave me alone. I'm going to do my science. When I'm ready, I'm going to come out, tell you what I've done. No way. The public would not have it. And I realized that I had to make a change in the way we were doing work. And so we decided on the panel to open this study up to the public. I know that the Department of Energy was scared to death when I made that decision, but it turned out that was the only way we could have salvaged this work and had the credibility that we had at the end. And we never compromised classified material at all. Declassification of the records. I had personal support from Admiral Watkins, who was the Secretary of Energy at the time. We involved Native American tribes because they're a huge component of the area and so important. And we focused on risk communication and stakeholder participation. Those things were really unprecedented in this science until this study was undertaken. And we would not have succeeded without taking those steps. I'm going to tell you quickly a story about Tom Bailey. And if you heard this last year, you know, it's just a repeat. But after I was in this for a year, I was really discouraged. We were getting really bad press. None of the public were supporting us. The Native Americans weren't supporting us. And so I was just looking for something to give me hope that we could succeed. And there was a guy that came to all the meetings, and he was very vocal. I got to meet him. His name was Tom Bailey. He was a farmer. He was a farmer that lived not far away. And he was very critical of what we were doing. And after about a year, he called me up and he said, "John, can you come out early to the meeting?" He said, I want to talk to you about something. So I flew out to the meeting, and he actually called a press conference. And he said, I did not know this, but he called a press conference, and I'm sitting there with him. And he said, "John, I think you're going to succeed at this." So this came out in the newspaper where Tom Bailey, sitting on the left side there, endorsed the work that we were doing. And this is what the press said. This is from Tom Bailey. You'll never imagine how important that was in my career as a scientist. The one guy that stood up for me meant everything. And he presented me with this bottle of milk. It was empty at the time. And he said, "I want you to have this sort of as a memo of this press conference." And he said, "By the way," he said, "if you look at it, it says that the phone number for the Twin City Creamery, Pasco and Kennewick and Richland is 131. Iodine 131 was what was released from Hanford. So this was pretty special to him, and he left that with me. I'll never forget it. We were, in the end, successful at Hanford. So what I learned, trust and credibility, and you're going to face this all the time, especially if you're talking to the public, but also with your peers, all right? Trust and credibility, it has to be based on data and science. It has to be transparent, it has to be effectively communicated, and it has to be earned. And finally, You got to go beyond what's expected of you. I want you to take that away. You can't just go out, crunch the numbers. You've got to look for opportunities that are beyond what's expected of you. And that's how you build trust and credibility. I am so grateful to the Department of Energy over all the years, even though I've not been paid by the Department of Energy. It's kind of crazy. I've studied most all of their sites. These have been wonderful opportunities. But I'll tell you this, the dose reconstruction studies that I've done and others have done as well have advanced the science of risk assessment more than anything that I can recall in my entire 50-year career. So let's move on. Now I'm going to get into the 2000s, and this is going to pick up a little bit. I look at this as the value of risk assessment era, when we're finally realizing we can use these mathematical models and estimates of risk to do something of value. This is the Rocky Flats site out in Denver as it appeared about 20 years ago. If you don't know about this facility, this is where we made the plutonium. It's between Denver and Boulder, Colorado. That was some of the most expensive land in the entire country, the fastest growing place in the country. And so the Department of Energy wanted to clean up the site. So the contamination came primarily from plutonium that leaked from drums onto the soil, and then it was dispersed by the wind around the site. And if you look at the site, this is just a map of where the contamination existed. And if you remember anything, I'll come back to this, but somewhere between 930, 3,700 becquerel per kilogram, all right? If you look at that color, everything in yellow and red and pink, and that color represents the area that was ultimately cleaned up out of 6,000 acres. All right, how did we get to that point? I was asked by not the Department of Energy, but by the advisory team, public advisory team there at Rocky Flats, to bid on a piece of work to assist them in coming up with a cleanup level. So what DOE did was they went to the Citizens Advisory Board and said, will you pick a scientist, pick a team to help us come up with a cleanup level that you think the public can accept, okay? So I was hired to do the work. We're working with members of the public just like this. Some of the objective was to come up with a level of plutonium and other actinides in soil such that subsequent human exposure during future use of the site does not result in levels of radiation dose that exceed specified limits. I'll go over those in a moment. And these are called RSALs, radionuclide soil action levels, okay? The criteria, 0.15 millisieverts, that's 15 milligrams. So that was what the dose could not exceed, okay? We had to have unrestricted use of the land, a 1,000-year time frame, use of available site-specific data, account for uncertainties. We'll come back to that in a moment. And the support of the Rocky Flats Citizen Advisory Board. Okay, so basically what we're doing, if you think about this, you've got the contaminated area, right? You're given these criteria. Now you've got to work backward. You have to work backward using your mathematical models to come up with a contamination level that doesn't exceed the 0.115 millisievert dose. Does that make sense to all of you? Okay? But, you know, there's a kink in this. The kink is that you've got a panel of the public at every meeting watching what you're doing, and you have to convince them. You have to help them understand what you're doing. And ladies and gentlemen, this is tough stuff, believe me, okay? Some of these members of the public were activists. Some of them were scientists that really understood some of the science, okay? And I'll tell you one story about uncertainties. Because when you hear uncertainties, to many of the public, you're terrified, okay? If you're going to calculate something, a level, but it's going to be uncertain. I don't want to have anything to do with it if you're not certain, right? I want you to be certain. Well, we know in science that it just doesn't work that way, okay? And so we spent a number of our meetings explaining what uncertainty was all about. And this took us over a period of about 6 months to really have our process accepted by the public, that just because it's uncertain doesn't mean it's not good or reliable science, okay? Okay, so what I did, I went to the panel and I said, okay, how certain do you want to be when we decide on this level to make it acceptable to you? Now you can think in your own head what number you would throw out there. Do you want to be 90% sure? Do you want to be 100% sure? So what I did was to have them vote, not vote, but they wrote down their value on a piece of paper and they gave it to me, and I worked up the results. And you're going to be surprised by this. They said, I want to be 90% sure. 90% sure. Now, I thought for sure they were going to go 99.9% sure, 97.5% sure. I thought for sure it would be a much higher level, okay? But it wasn't. This is what they wanted, okay? What this does theoretically is it means you have a little more leeway in terms of the cleanup. So what we did, we came up with a system that's probability of exceeding the dose limit, which was 10%, right, as a function of the concentration of plutonium in soil. Also as a function of different scenarios of exposure, right? This was the rancher scenario. We looked at many different scenarios, but these are the two key ones, and the child scenario. And where those curves intersect the 10% level is your R cell. That's your R cell. When we got finished with the study, this was the answer. They all voted, not all in agreement, but the majority of the panel voted on the cleanup level, which was about 1,300. The actual level used by the panel recommended 1,300 becquerels per kilogram. The actual level used to clean up the site was 1,800 kilograms, becquerel per kilogram. Now think about that. From a practical point of view, there's no difference between those two numbers. They're very, very close, okay? But I want you to just read this quote. This is a quote by Clay Sell, Deputy Secretary of Energy. They cleaned up Rocky Flats for $7 billion. The projected cost originally was $29 billion and 70 years. This is what risk assessment can do for us if we apply it correctly. Huge, huge savings. If you go to Rocky Flats now, it's going to look like this. Cleanup is done. It's a wildlife preserve. It is one of the most pristine areas in the country right now, even though there are slight amounts of plutonium in the soil. Some people still don't like that, okay? But the risk is very, very low. That's the value of risk assessment. Now let's go into the 2010s, and I have two things to talk about here, data integration and the focus on risk. In May of the year 2000 at Los Alamos, there was a fire, Rio Grande fire, it was called, burned over 43,000 acres, I believe it was. 7,000 acres of Los Alamos burned. And we were asked by the Department of Energy to carry out a study looking at the risk to the public posed by the fire, subsequent to the fire, okay? And we learned a lot. The risk was very small, But one of the things that we really had trouble with was getting our arms around all the data. CDC had data. The lab had about 10 different divisions, kept collecting their own data. The Environment Department had data. So there was a lot of data collected during the fire and following the fire, but it was everywhere. It was everywhere. And when you have all these different databases, there's different nomenclature. There's no way all this fits together. We realized right off that was a huge problem for Los Alamos. So after this study, we went back to Los Alamos and said, you know, we'd like to try to help you get your data organized. If you could do that, you could do so many things. It would be so powerful. And so that's the project that we worked on for about 6 years called Los Alamos Risk Reduction Project. And we developed a process called RACER, Risk Analysis, Communication, Evaluation, and Reduction. And basically, I'll tell you what RACER is about, okay? You have data, but data really don't tell you much in themselves, right? You've got a concentration, a measurement somewhere, but it doesn't tell you what a dose is, okay? However, what we did do was to take all of the data at Los Alamos, consolidate this into a single database, consistent nomenclature, 10 million historical records that we put into the database. Now you got something you can work with. Data leads us to information. Location on a site, aerial coverage, exposure scenarios where people might access contaminated areas and so forth, but that's still not it. We have to convert it into knowledge. And knowledge is what we use to make our decisions. And so our theory with Los Alamos was to come up with a system that would take all their data once it's organized, all right, and at a push of a button, or you could circle a contaminated area or 3 contaminated areas and say which one poses the highest risk. And it comes back instantly. Now think how far we've come since 1970, okay? Huge, huge improvements. And now we're taking data, millions of records, we're putting it in one place. We're using it, we're tapping it to calculate doses. And that's what the Risk Reduction Project was all about. So we actually came up with software that helped us perform the risk analysis here on the left and to rank sources. And then you go through a process to account for cost, okay? Feasibility of cleaning something up, and all that was built into the software. And that was called source ranking by risk potential. And in the end, risk reduction, which this is the information you give to your managers. It's what they need to make their decisions about what to clean up first, how much it's going to cost. This is a beautiful piece of work. RACER still exists. It's not at Los Alamos, but it does still exist, and we use it in applications in a lot of our work. So I'll mention briefly in kind of closing this decade, one more study that's really important to me, very close to me personally, and this is the Atomic Veterans Study. We had over 200,000 veterans who were exposed to these atmospheric tests that I mentioned earlier. These were all volunteers, but they were part of the Navy, the Army, the Marine Corps, and they went out into these areas after we detonated a test, and in some cases minutes or shortly after these weapons were detonated, they marched into the areas. We wanted to know what their reaction was going to be. We wanted to know if we could protect these veterans while they were out there from radiation exposure. I mean, this was so primitive, it's crazy. But however, one of the things that we did is to take 115,000, and this is in working with Dr. John Boyce and a part of his million-person study, which is so important. I'll mention it again in a moment. 150,000 military veterans In our study, 60% of them Navy, 23% Army, 11% Air Force, and 4% Marine Corps. Okay, so what we did was to calculate doses to all of these individuals. We really focused on a 10% slice of these guys, but we can expand that to the rest of the population. This is of huge, huge importance now because we've never been able to study the veterans. We've compensated them since the early 1980s for what they did for our country, because they truly were heroes, right? But we never knew whether or not they'd have a higher incidence of cancer, okay? The Defense Threat Reduction Agency helped enormously because they declassified these records for us and made them available to use in our study. Now, I don't know how well you can see this, but I want to point out a couple of columns. This is the mean individual dose, and it's by the Nevada Test Site and the Pacific Proving Grounds, all right, and by military branch. I want you to look at these doses here, the mean doses. These are in milligray to the bone marrow. Look how low these doses are, okay? This is the largest low-dose study with good dosimetry that we've ever done, that has ever been done, if I'm not mistaken, all right? The Atomic Veterans. And look at the coefficient of variation here. This is a factor of 2. This is phenomenal, ladies and gentlemen. These are incredibly high-quality doses, a large population group. And so what did we find? No evidence of a higher incidence of cancer among this group that we've studied. Now, this is just a small part of the million-person study, and we have to do a lot more work. We need 1 million people to get the statistical power to understand what radiation does to people, okay, at low doses. But this is a huge component of the work. I'm very proud of what we've done. And I want to make it clear that in terms of compensating the veterans, I would never, ever think we ought to suspend that program, ever. Those were heroes. They deserve everything that they're getting. The good news is we can now tell the veterans that they don't have a higher incidence of cancer caused by what they did for their country. Okay? So where are we going? So listen to me. If you think I've done all the work, ain't no way, okay? I've just been lucky. I've been so lucky in my career to have an opportunity to do some of these great, great studies. But we have a long way to go. And you ladies and gentlemen sitting out there, I want to tell you that there's as much to do in the next 50 years as I've had to do in my 50 years. And I envy every one of you. I wish I could start over. Validation. I'd work more on validation. And what I want to know, I want to be able to prove that these models work. And we've come a long way on this. And we have a lot of studies that we've done and others have done to confirm that these mathematical models really not only predict where this material goes in the environment, but also the doses. Communication, we need help. We need a lot of help in communication. We're still terrible at this as scientists, and I make my team, I tell them all the time, whatever you do, you have to be able to communicate to the public yourself and explain it to people. Data risk integration, you know, we need to be able to calculate risk in an instant. And I'll tell you this, you know, I told you about TMI and what a problem we had coming up with the dose at TMI. We're doing some work for a large nuclear corporation, Exelon, and we have come up with a way to calculate dose automatically and instantly if they have a release. And we're tapping into the meteorological data 24/7. Anytime they have a release, if they want to know if they have some release of a radionuclide, whatever the amount, and they want to know, well, is this anything to worry about, they can use our software to calculate the dose to the public within minutes. This is where we are. This is where we are. And risk-informed decision-making, like Los Alamos, we have a long way to go in this. And then finally, the resolution of linear non-threshold. I didn't talk about that much, but basically low doses of radiation to people. And what does it really mean? Okay, we are going to solve this problem over the next decades. I'm going to quit with that, Scott, and I do appreciate your patience and time. I'm just about right on the time, I think. Are we good?
That was outstanding.
Yeah.
I'm really glad you guys got to participate in John's lecture. A couple of things, just to tell you how this lecture series started. 3 years ago when I started working for SRR, I took a handful of interns to John's farm. We had lunch with you. We got to see a 1,000-acre farm. You guys were delightful. It was, I think it was a highlight of the interns program. We had a great time. We wrote it up. It was published. We had photographs, and we thanked you very much for that. It was outstanding. Yeah. Last year posed challenges to us, though, because our internship population was very limited because of COVID. And so we started thinking about how are we going to overcome this and still give a program to our interns. And so we started thinking about new technologies, and it was WebEx. Leslie Wooten, she became an expert in WebEx. We had multiple presentations. They were all recorded on WebEx. We wanted to share it. And Dan Skiff was there, Keith Liner, my staff as well. We wanted to share this and broadcast it out. So we did to other universities. They would have been here, but they couldn't. But we still shared it with them. But we also shared it across the DOE complex, both at headquarters and other sites. I think it was very well received. We had outstanding presenters. And so it also helped us to figure out, to overcome something that we thought might have been insurmountable. This year, we hope the same thing happens. It's going to be phenomenal for you. We're recording it on WebEx. We're broadcasting it out. We're also video recording it. And we're going to put this on a YouTube channel just like we did last year. And that way it'll be available to anybody who wants to see it. So our speakers, the next three are going to be only on WebEx because our speakers, they live across the country. Next week, we're going to have a speaker that's going to talk about designing nuclear propulsion systems to support NASA's mission to send man to Mars. That should be phenomenal. We also have a nuclear engineer that I'm knowing quite some time. He was the nuclear engineering officer for the state of Pennsylvania. He was actually in the control room at 3 Mile Island, melted down. He was the advisor to the governor, and I think you'll really like his perspective. And then we also have a health physicist who's also an attorney, who's done work for the National Academies of Science, and she's going to talk about 2 reports that she's helped prepare on the Fukushima Daiichi accident. And then lastly, I'm going to be giving a presentation here, but I'm going to talk about the importance of volunteering for professional organizations, and at least from my experience, how that led to truly influencing the establishment of standards for protecting disused sealed sources. And so, John, I got 2 questions for you, and I'm going to ask them one after the next. Okay. But when you guys ask the questions in the field, John, make sure that you repeat the questions because we might not be able to capture it on the recordings. So the first question is, we all face diversities in our career. And I think the real measure of success is often not that you had to face diversity, but you found ways to overcome it. And I know you probably have some success stories. And then lastly, the second question is, what's the single piece of advice that you could share with our summer interns that will make their careers both rewarding and successful?
Good. Just hold it. That way I'll give it back to you. Okay. Let me first take your second question. I want this to be the one thing that you remember when you leave this room. I'm a scientist. I'm a problem solver. Basically, that's what I do, is solve problems, right? But you do it in a certain way, a scientific method.
Attention all personnel. A report has been given of an injured person in 704 room 21S. Room 21. Emergency response people, please respond to 704 room 21.
Okay, hopefully that's it. But I want you to remember this. As you go to solve your problem, break the mold. Don't go try to pull a model off the shelf without thinking about it. And as you try to solve that problem, try to figure out a new way to do it. And in all of my career, in every one of these studies, solving these problems took new thinking. Not just pulling something off the shelf and doing it, but I want you to break the mold. Okay, does that make sense to you? I want you to think in new and creative ways of solving problems. That's my advice, okay? I've had some great successes in my career, disappointments. I think out of all of what you heard today, I would like, my greatest disappointment was Los Alamos. I had a wonderful time there. The laboratory was so supportive of what we were doing, but we didn't quite get to finish and see the methodology that we had developed for making risk-informed decision-making as a part of everyday life. And we still have a long way to go in that. Now, on the other side of this, you know, I talked about the data being put into one database, the 10 million records and so, and that all still exists at Los Alamos.
Attention all personnel, attention all personnel. A report has been received of a person needing medical attention. First aid team and incident scene coordinator report to 704 Sierra, room 21. Non-essential personnel remain clear of this location. Attention all personnel, attention all personnel. A report has been received of a person needing medical attention. First aid team and incident scene coordinator report to 704 Sierra, room 21.
Okay, but the bottom line is we succeeded at Los Alamos in a lot of ways. Okay, in particular, I believe now here at Savannah River, you've been working for a year to consolidate all of your data into one database, and the department is encouraging this across all of the different facilities. So if we made some impact on that decision by the department, then I've succeeded, okay? Now, how do we want to handle the questions? Do you have questions?
Please ask questions.
And don't be afraid. Okay, so the question was, when I went to the cabin, right, did I hear it correctly, and got the catfish, did we put emphasis on those studies? And the answer is yes, they're already being studied. In fact, we had experts at Oak Ridge who spent their careers studying the uptake of radionuclides in fish, including catfish, all right? And actually, when we looked at it, that was a significant pathway of exposure. That was the significant pathway of exposure for the cabin, the folks in the cabin, okay? Yeah. And the young lady, epidemiologist, you had a question back there? Okay, yes, ma'am. And I couldn't, I'm a little hard of hearing. Absolutely not. I would have been terrified, and I might have been shot if I'd have gone back there, okay? That was a true story. That was a true story. Yes, ma'am. How do you get access to the Atomic Veteran Study? Oh, ethics. Are you asking the question about do we worry about ethics and so forth? Oh, absolutely. And you know, you're going to be an epidemiologist, and you're going to learn a lot about this, okay? In a study like this, we never know individuals. We only have numbers, all right? What we do know is that we may have a number of a person, and we know their rank, their rating if they're in the Navy, okay? And all of this information helps us to create an exposure scenario, all right? And all of that is approved by special boards at the universities. All of these studies have to be approved just to make sure they are ethical, okay? Very important. You'll learn a lot about that. Yeah.
Especially for people in the nuclear community or entering the nuclear field, what's the best piece of advice you could really give about actually communicating meaningfully information to the public? Since I know you've worked with that.
I have, and I tell you, that's probably one of the more disappointing aspects of the work that I've done over the years. We have to keep trying, and we have to keep trying new methods to communicate with people. And I personally believe that this can't be turned over to public relations. This has to be done by us as scientists. And so that's the best advice that I can give you to take away from this, is that it's our job. It's our job as scientists to communicate what we do. Now, the PR people are specialists, and they can advise us. And on the Hanford study, on a Rocky Flats study, we had professional advice about how to communicate our results before we went out and talked about them. But nevertheless, I had to go do that, okay, or other people who were a part of the team had to communicate that. But I don't know all of the answers to communication because we seem to be quite stagnant about this.
Has the Fukushima dose reconstruction been completed? How long did it take to complete the study? And where can your study results be found?
Okay, well, the dose reconstruction on Fukushima, to my knowledge, has been completed, all right? I was not a part of that, but the Japanese have carried out extensive studies on estimates of dose and risk to people, all right? We have worked on Fukushima. We have carried out an analysis of exposures to military personnel who were on the ships, who were in the plume and so forth. And that work we're finished with, but we haven't published yet. Okay?
One more online. Yes. This is an intern from here this summer who's participating online. They were wondering what sector holds more opportunities for up-and-coming professionals, private versus public, in risk assessment.
I'm not sure I understand the question. What?
I guess for a new career, if you're going into the industry, would you recommend private industry versus public industry for risk in the risk assessment?
Oh, if you're going in, what opportunities?
Yes.
Well, look at the opportunities that I've had, okay? I'll tell you, it's a tough business, and there are a lot of consultants in this business. A lot of them have been around for a long time, and a lot of them have converted their own small business into large companies, and they've been very successful. It's all a matter of timing. It's all a matter of the people you have working with you. But the opportunities are phenomenal. And you think about things like my corporation, who works virtually from all over the country. So my team live where they want. That's the hardest decision they have to make, is to figure out where they're going to live. So I think the opportunities are just incredible.
One more. Can you tell us about your initial interview with ADM Rickover?
Well, I'll try to answer this very quickly. It was very short. It was very short. I was in his office no more than 2 minutes, and he kicked me out. He said that I had made a grade. I've forgotten what it was. It might have been a C. It might have even been a D. I don't know what I had, but he was very upset with that grade, and he said, "You don't study enough. Why do you want to be in my program? Get the heck out of here." Those weren't exactly his words. They were a little bit more profane, to be honest with you. And you just quietly, "Yes, sir," you turn around and you walk out. And then they put me in a box, a place where there was one desk and one chair, and I sat there for the rest of the afternoon. That was about 3 hours. Nobody said a word to me. I knew when I left the interview that I'd failed, but I was accepted to the program. There are more stories that I could tell you, but we don't have time. Thank you.
And with that, thank you very much for attending. Let's give John one more round of applause. And John, thanks a million.